Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on complex analysis, complex integration lecture number 2, in which I will give the concept of line integral in complex plane. Now I will give you the concept of line integral in complex plane. Let xy be a complex plane, C be a rectifiable arc, AB. Fz equal to u is the function of xy plus I, v be the function of xy, be any complex function. Let us partition the arc C into a number of subinterval. Zk minus 1, Zk, k equal to 1, 2, n. Let xi k be an arbitrary point in any subinterval Zk minus 1, Zk. Let us take limit of sum sigma k equal to 1 to n function of xi k delta zk, where delta zk equal to zk minus zk minus 1. Let this is number 1. Since 1 be the limit of sum for the first partition P1. Similarly, corresponding to each partition, we may get limit of the sum. Taking norm of P, partition P tends to 0, delta zk tends to 0, and n tends to infinity if the limit of the sum limit n tends to infinity sigma k equal to 1 to n function of xi k delta zk is a finite quantity Then let this is 2. 2 is called the line integral in the complex plane corresponding to arc C, and it is denoted by integration along arc C fz dz, that is integration along C fz dz equal to limit n tends to infinity sigma k equal to 1 to n f xi k delta zk. Now we solve a problem. Problem is using the definition of integral as the limit of the sum. Evaluate the following integrals. Number 1. Integration along the rectifiable arc C dz. Number 2. Integration along C modulus of dz. Number 3. Integration C along C z dz, where C is any rectifiable arc joining the point z equal to alpha and z equal to beta. Now we solve this. Since from the definition of integral as limit of the sum, integration along rectifiable arc C fz dz equal to limit n tends to infinity sigma k equal to 1 to n function of xi k delta z k. And this is number 1. Now we solve number 1. Integration along C dz. Here fz equal to 1. Therefore, integration C dz equal to limit n tends to infinity sigma k equal to 1 to n delta zk. Since f xi k is 1, this is 1, implies that integration along C dz equal to limit n tends to infinity sigma k equal to 1 to n, and delta zk means zk minus zk minus 1 equal to limit n tends to infinity. Here k equal to 1, z1 minus z0, z1 minus z0 plus k equal to 2, z2 minus z1 plus plus zn minus zn minus 1. Here z1 cancel. In this way z2 cancels. Only remains limit n tends to infinity zn minus z0 equal to zn. The last point is beta minus z0 initial point alpha. Number 2, integration along C modulus of dz. Here also fz equal to 1. Therefore integration along C modulus of dz equal to limit n tends to infinity sigma k equal to 1 to n. Here fz equal to 1 delta zk modulus. This equal to limit n tends to infinity sigma k equal to 1 to n. This is modulus of zk minus zk minus 1. Implies that integration along C modulus of dz equal to limit n tends to infinity. Here for k equal to 1 we get z1 minus z0 modulus plus k equal to 2 modulus of z2 minus z1 plus plus modulus of zn minus zn minus 1 bracket closed. This is equal to limit n tends to infinity modulus of z1 minus z0 means length of chord z1 z0 plus length of chord z2 z1 plus plus length of chord zn minus 1. This equal to limit n tends to infinity. This length of chord means length of arc. Since this chord is very small, length arc z1 z0 plus length of arc z2 z1 plus plus length of arc zn minus 1. This is the sum of all arcs, means total length of the arc. Total length of the arc. See, number 3, integration along C z dz. Here fz equal to z. Therefore, integration along C z dz equal to limit n tends to infinity sigma k equal to 1 to n xi k be the point in zk minus 1 arc, and dz means here delta zk. Let this is number 1. Let I equal to integration along C z dz. This is number 2. Therefore, 1 may be written as I equal to limit n tends to infinity sigma k equal to 1 to n. Since xi k be arbitrary point in the interval zk minus 1, so we may write here zk delta zk means zk minus zk minus 1. This is number 3. Similarly, I equal to limit n tends to infinity sigma k equal to 1 to n. In place of xi k, we may also write zk minus 1, since it is arbitrary point in the interval zk minus 1. So here we may write this is number 4. Adding 3 and 4, we get I plus I, 2i limit n tends to infinity sigma k equal to 1 to n. Here we see zk minus 1, here also same, we take common zk minus 1, here remains zk, here remains zk minus 1 equal to limit n tends to infinity sigma k equal to 1 to n zk square minus zk minus 1 square implies that 2i equal to limit n tends to infinity. Here if we put k equal to 1, this is z1 square minus z0 square. If we put k equal to 2, z2 square minus z1 square plus dot plus plus zn square minus zn minus 1 square closed. Here z1 square cancel. Similarly, z2 square and z2 square cancels. Ultimately remains limit n tends to infinity zn square minus z0 square. This is equal to, since zn the last point is beta square and z0 be the initial point be alpha square, implies that I equal to half beta square minus alpha square. Let this is number 5 and this is number 6. If C is a closed curve, then Zn equal to Z naught. Putting these value in 5, we get 2I equal to, since here Zn equal to Z naught means this is 0, right side 0, implies that I equal to 0, implies that integration along the closed curve C, Z dz equal to 0. This is an important result. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.